Okay, real quick, I wanted to talk about where everybody should be as far as homework and videos and stuff like that. So I know we did not have a live lecture last week. Well, we did last week, but we did not on last Thursday because something came up with me, so I couldn't come to a live lecture on Thursday. So anyway, for Thursday, Friday, what you've got is on YouTube. There are two separate playlists that we're kind of dealing with right now. So there's on YouTube, there's the playlist Calc 2, it has a long name, but Fall 2020 lecture videos. And then it says after exam 2, before exam 3 or until exam 3 or something like that. And so if you go in there, that's where I'm posting all the current videos. If you go out to the playlists on this YouTube channel, it's just where I post everything. Then you can go see like all the videos from each exam. But anyway, on that are kind of the required videos for last Thursday. There are three of them, but they're short. So one of them's 15 minutes, one of them's 7 minutes, and one of them's 32 minutes. So anyway, all together, that kind of covers what we would have done Thursday. So the three videos for Thursday are called Unit 3 Video 3, and then there's 4 and 5. And on video 3, there's a little bit of overlap with what we had already covered, but it probably won't hurt to review that. But there should be some new stuff in video 3. And then video 4 would be mostly new, or basically all new. And then video 5 is on monotonic and bounded sequences, which is not like the most important topic ever, but it is something that you want to make sure you have covered. We're not going to talk about it in a live lecture. We could definitely talk about it in like the review session before the exam. And then if you want to come to office hours or stick around after, I'm happy to go over stuff like that with you. But those three videos are going to replace last Thursday's lecture. So do make sure you watch those. Because I wasn't live and because I didn't get the WebAssign assignment up, we're not going to require a separate WebAssign. So for homework for right now, okay, on WebAssign, there's only one right now, and it's due tonight. And that's called Sequences 1.
Was that the one with like all the questions and whatnot?
Yeah, it's like a lot, but they're pretty fast, I think, right? Yeah, there's probably like 25, 30, maybe even a little bit more, but they don't take as long as integrals. Like this assignment, I don't think it takes you that long, even though there's a lot of problems. So that's the only WebAssign. That one is due tonight. So just make sure you get that done if you haven't already.
That one only took me like 45 minutes, so it's not too bad.
Yeah, it's not like terrible. I mean, it's not going to be, a 10-minute thing, but it's not like, it's probably quicker than like the trig sub assignment, even though that one probably only had 4 or 5 problems. So yeah, I think it goes pretty fast. But then there are some worksheets you guys need to be doing, and we're going to be doing more of these as we keep going through sequences of series. These are in Google Drive. And I'm probably not going to collect most of this stuff. I might have you hand in a couple on CrowdMark, but what's going to happen with the worksheets is I'm going to give you solutions to them. So even if you hand them in on CrowdMark, I would have you do that just to get credit for doing them. So like I would go through, make sure you did it. I would give you, and we'll do that for some because I think it'll help your homework grade. And it helps just have to write it out. But if you do hand it in on homework, it would not be corrected. It would just be checked off that you did it, basically free points for having done it. And you're expected to use the solutions to make sure that you do genuinely understand how to do the problems on the worksheets. I'm not going to collect the two from last week, but there are two from last week. One is called Sequences 1. So Sequences 1 and then Sequences 2. Those two worksheets are in Google Drive. So if you go to Google Drive, we're in Unit 3 now. These are in folder 1. And the names of the files I think are pretty clear, but usually what I do is I put one file in that is the worksheet itself, and then a separate file with the solutions. I think for sequences 1, it's all in the same file, but you can kind of go in there and see. You should for sure be doing those. So especially on sequences 2, there's stuff on there that's probably not on that WebAssign. And then some of the stuff at the end of sequences 1, same deal, where it's harder than what's on the WebAssign. Not that we couldn't do a WebAssign, but we didn't do the WebAssign. So you just have the worksheets on that. That's going to happen with some of the series stuff too. So there'll be some WebAssign, but it'll be more worksheets with solutions where, okay, you're going to be kind of trusted to go do the worksheets and make sure you understand where you're given the solutions, but come ask if you're not sure how to do something. If I do collect something on CrowdMark, so like I said, nothing from last week, but starting this week, there may be some that will be collected on CrowdMark. If I do, you at worst have to copy it over in your handwriting. You can't hand me my own solutions, but you can use the solutions to help you as much as you want. But you do need to make sure you understand them, that you're not just copying them without understanding what's going on. Okay, so anyway, for last week, just because I didn't get to meet with you guys live, I just wanted to make sure it was clear what we should be doing. So you have those 3 videos from Thursday. So that would cover Thursday. Let's write that. So, we had the live lectures Monday through Wednesday. That would cover Thursday. Like I said, all those together still probably about an hour, a little less than an hour. And then you've got the one WebAssign due tonight, and then you have these 2 worksheets. There was also a take-home quiz early in the week that you should have already done that. But that's the homework that covers kind of what we were doing last week. Additionally, there are 3 prereq videos. So there's a playlist on that YouTube channel called Prerequisite Material for Sequences that I would strongly recommend that you watch if you haven't already. So there's one on absolute value, there's one on finding formulas, and there's one on factorials. I forget the order of these, but there's one on finding formulas, there's one on factorials, and then I just said what it was, but I forget now. Finding formulas, factorials. What's the third one? I just told you guys. Absolute value. And so we talked a little bit about that stuff last week, not as much on the formulas, but that's something for sure you should look at. And then we talked a little bit about factorials and absolute value. Those go into a little more detail on those. They're not super long, but they're definitely worth watching. It's stuff that kind of you're expected to know from before, or you're expected to kind of figure out on your own that I think is maybe not obvious. And so I would look at those if you get a chance. Okay, that will bring us up through the end of the stuff that we're going to cover on just sequences. We're going to start today looking at series, but I did want to make sure that all of this was clear. Is everybody clear kind of where we are? Because like we said last week, it made a big deal of this does build quickly. So it's important we understand, especially the big ideas from last week before we move on. Any questions? You guys good? Okay. All right, so then what we're going to start talking about is series. And we talked a little bit about series last week at the very beginning. So that was kind of the idea of the take-home quiz, was this idea of a sequence versus a series. And so I want to kind of talk about that again, and then we're going to get into how do we deal with series, because it turns out there's a lot of applications of those, and there's a lot of things we're going to want to do with those as we go on. So the first thing I want to look at is this sequence A sub n, and we've looked at this one before, and we'll probably talk about it again at some point, but this is an easy one to start with. So I want to look at that sequence an equals 1/2 to the n, and then I also want to talk about this sequence Sn equals the sum k equals 0 to n of 1/2 to the k. And so these are 2 completely separate sequences that are related to each other, but they are two completely different sequences from each other. So the one on the left, if you start just listing terms, we can quickly figure out that, okay, A0 is 1, A1 is 1/2, A2 is 1/4, A3 is 1/8, A4 is 1/16. And so this is the list of numbers: 1, 1/2, 1/4, 1/8, 1/16, and so on. Does that make sense to everybody? That's clear. Okay. And so the kind of explanations or brief proofs that we were doing last week were showing whether something like this sequence converged or diverged. And so we said last week that this one converges to 0, and this was a quick one because it's one where it's an exponential and the base is between 0 and 1, until we said, okay, when that happens, we know that as n goes to infinity, the whole thing goes to 0. And so most of last week was devoted, or most of the talk we've done so far was talking about how you tell whether one of these sequences converges or diverges, and the different techniques in order to prove that when they get more complicated than this. Does that make sense to everybody? Any questions so far? Okay, and so now we also have this type of sequence on the right that we haven't talked as much about, but it's still a sequence. It's just defined using this sigma notation. And so we can talk again here about S0, S1, S2, S3. We can go as high as we want, but I want to start with S3 just because it's easier to see what's going on from the higher ones than the first couple of those, or the first three of those. So S3, and again, we talked about this quickly last week, but where would I plug in 3? Does that go in for n or k or both of those? What is the 3 here? What is that?
Is it n?
Yeah, it's n because it's Sn up here. So when you talk about S3, that's the sum from k equals 0 to 3 of 1/2 to the k power. And then down here, S4 is the sum k equals 0 to 4 of 1/2 to the k power. And it's the same thing for 0, 1, and 2. But this is the definition of what S3 shows you. Just like over here, A3 is really, okay, you're replacing n with 3. It's 1/2 to the third. That happens to simplify to 1/8. Well, okay, this is what S3 means. Now we need to figure out how to simplify it. So we're going to get a number. It's not 1/8, but we're going to get a number like 1/8. And just real quick review, sigma notation means, okay, we plug in 0 for k, so we get 1/2 to the 0, that's 1. We plug in 1 for k, that's 1/2 to the first, that's 1/2. Plug in 2 for k, we get 1/4. And plug in 3 for k and we get 1/8. And sigma means we add all those. Does that make sense? Any questions so far? Okay, and if we add those up, we get 15/8. And then for k equals 0 to 4, that's 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, which is 31/16 if we were to get a common denominator and actually add all those up. Any questions on what we're doing over there on the right? You guys good? Okay, so S0 is the sum from k equals 0 to 0 of 1/2 to the k. That means you just plug in 0 and stop. There's nothing to add. So you plug in 0 for that and you get 1 and then you're done. And then this is the sum from k equals 1 to 1, or I'm sorry, k equals 0 to 1 of 1/2 to the k. That's 1 plus 1/2, which is 3/2. And then the sum from k equals 0 to 2 of 1/2 to the k. That's 1 plus 1/2 plus 1/4, which is 7/4 if you get a common denominator. So again, this is a list of numbers: 1, 3 halves, 7 fourths, 15 eighths, 31 over 16, and so on. Does that make sense? Any questions? Nick, that's a really good question. And I didn't mean for you guys not to be able to post that publicly. If you don't care, post that in the chat, and then let's talk about that in a couple minutes. If you don't care to post it to everybody, or I can type it over, or we'll just explain it in a minute. It should let you now post that to everybody. But we will talk about that question, but give me a minute on that. Any questions on how we're computing these things? Okay. And so this thing on the right, it is still a sequence. So this is a sequence. But we call it a sequence of partial sums. And the reason we call it that, it's partial sums of these. So like a series is when you add all these. So instead of 1, 1/2, 1/4, 1/8, 1/16, it's 1 plus a half, plus a fourth, plus an eighth, plus a 16th, plus 1 over 32, plus 1 over 64, plus forever is an infinite series. If you add them all up forever, these are called partial sums. So S2 is called the second partial sum. That means the sum from wherever you start. Here we're starting at 0 until 2. This means the sum from wherever you start until 4. That's what S4 is. It's called the fourth partial sum. This is the sequence of partial sums. Series, it's actually a little bit ambiguous in the book is that how they actually define a series. One good way to define a series is the limit of the sequence of partial sums. So if you look at this limit, if you look at what's going on, it's actually easier probably to think of this as mixed numbers to kind of see what's going on. When we list these as mixed numbers, what does it look like this is doing? Is that converging or diverging? And if it's converging,
getting very close to 2.
Yeah, it's getting very close to 2. So we have not proven this, but we can show that Sn approaches 2. So Sn, this sequence of partial sums, converges to 2 in this case. In no way is this a proof of that, but it looks pretty clear that that's what's going on. The next one, if you think about the pattern, is going to be 1 and 31 over 32. And the one after that's going to be 1 and 63 over 64. So these are getting infinitely close to 2. This is a pretty convincing argument that that's what's happening. It's not a proof yet. We're going to get to that, but this converges to 2. Does everybody follow that? Any questions? And Nick, I know that question's in the chat, and everybody should open up the chat and read that question. That's a super important question that we're going to get to. But aside from that, do we understand what's going on with this? Okay, so both of these are examples of sequences, but normally when we're talking out loud and when we refer to a sequence, we're talking about one like this on the left. This is what we were talking about last week. And the main difference is you can quickly get any term you want. So like if you wanted a sub 93, like if I randomly wanted you guys to find a 93, you can do that here. So you would just plug in 93. Over here, if you wanted to find S93, there's not an easy way to do that, or at least not a quick way to do that. We don't have what's called a closed form to find this. Here, I can just plug in 93 and be done. Here, I plug in 93, but that means I'm adding up 93 or 94 terms in another sequence. So there's not like a quick way to get this based on what we've done so far. Over here, it's the sum. This, when we say Sn converges to 2, we're saying the series converges to 2. We could also write the limit as n goes to infinity of the sum k equals 0 to n of 1/2 to the k equals 2. This, all three of these, this statement, and this statement, all mean exactly the same thing. All of those can be used, but the most common thing to say is actually not that. Normally what we write is the sum k equals 0 to infinity of 1/2 to the k is equal to 2, or we say that converges to 2. This notation on the bottom right, that's the most common notation to indicate that the series converges to 2. And when you say that, what you mean is that this sequence of partial sums gets infinitely close or arbitrarily close to 2 as n approaches infinity. Does that make sense to everybody? Any questions? Okay, and then let's talk about Nick's question in chat. He says that if the sequence converges, meaning if this sequence over here is converging, does that mean the sequence of partial sums then, or this corresponding series, does that necessarily converge? The answer to that question is no, and we will see that later. It's possible. So when this converges, it's possible for this to converge, but it does not have to. And we will kind of see a lot of examples of that. That's kind of the basis of what we're going to be doing for the next several weeks. That's a super important question. Does everybody understand what he's asking? And then I have not explained why it's no, but the answer to that is no. But real important question. Other questions so far? Okay. So what we want to look at is we're going to look at specific series, and we're going to look at, okay, how do we know whether the series converges or diverges? It turns out that ends up being really important for stuff we're going to do later. And then actually in other sciences, series are used in a lot of places where you would not think they're used. And so we want to be able to tell whether a series converges or not. The techniques for that a lot of times might be easier than what we were doing last week, but they're weirder than what we're doing last week. The reason they're different is because on last week's problems, we always had a quick formula for a sub 93 or some random term in the sequence. Here we don't. What we have the formula for, this 1/2 to the k, that's the formula for this other sequence. So we can tell what that does, but that may not mean that it's easy to tell what this does. There's probably not an easy way to look at this and know, okay, well, I think there is an easy way to look at this and know that this sequence goes to 0, but there's not probably a good way to look at this and know for sure that that goes to 2, or at least not based on what we've done. And then if I change this from k equals 0 to k equals 1, that completely changes what it converges to. So it still converges, but it no longer converges to 2 because you lose this very first term. And so there's not a good way right now to look at that and know yet whether or not the series converges. And if it does converge, there's not a good way to know what it converges to. So that's what we're going to be working on. So the first type of series that we're going to look at is a geometric series. This is an example of a geometric series. Can somebody remind me what a geometric sequence is? We talked about that a little bit last week, and then in some of those prereq videos, we talked about that. So what makes this sequence geometric, which would mean that this corresponding series is geometric? Anyone know?
We use multiplication.
Yeah, we use multiplication. So to go from one term in the sequence to the next, you multiply by the same thing. So to go from 1 to 1/2, you multiply by a half. To go from 1/2 to 1/4, you multiply by a half. 1/4 to 1/8 times a half, and so on. That's not what happens on these terms. So over here, the sums don't get multiplied, but the things you're adding do. So we call this a geometric series because the things that you're adding get multiplied by the same thing every time. Does that make sense? All right, and so there's a clear pattern here on a geometric series. So on the partial sums, there's a clear pattern. We're going to try to determine what that is. And so I'm going to look at a different one, not the 1/2 to the n one, but I want to look at the sum k equals 0 to infinity of 1/5 to the k, just so it's a slightly different example from the one that we just did. And the goal on this is going to be to find a formula for something like this. So I want to be able to find a formula for Sn where you can just plug in like 93 and be done with it and not have to deal with sigma notation. Does that make sense to everybody? Okay, and just kind of as a heads up, what we're going to be doing for the next several minutes, so for the good bit of the rest of today's lecture, it is super important to understand what we're doing. And it's important enough to where you may be asked about this explicitly on an exam. So I do want you to understand this thought process for the next several examples. So this example and the next example. But what we're doing for this example is the proof behind what we're going to be doing for the next several days. And so the standard method for doing this problem is not what we're about to do. This is the proof as to why what we will do later works. Does that make sense to everybody? So like we're going to do a lot of weird stuff and you do have to understand it, but it's not what you would do on a normal problem. It's not like the quick solution. We're getting to a quick solution. Does that make sense? Okay. But please do follow along. Please do ask questions because this thought process and this proof is super important. So what we're going to be doing is we're going to find a formula for Sn. And Sn is the nth partial sum, meaning if you start at 0, rather than going from 0 to infinity, you go from 0 to n. So like if I wanted you guys to find like S4, that would mean go from 0 to 4. And it's not always 0, but this one is. So whatever it starts at until whatever this n value is. So S4 would be 0 to 4, S1 would be 0 to 1, and so on. Sn is 0 to n. Well, let's figure out what that looks like. So n will assume is a big number like 100 or 100 billion or something bigger than that. And so we're going to go from 0 to whatever n is. Well, if I start plugging in 0, I get 1. And then if I plug in 1, I get 1/5. I plug in 2, I get 1 over 25. I plug in 3, I get 1 over 125. And that keeps going. If I plug in 4, plug in 5, plug in 6, I get more and more things that I add up. But if I'm doing n terms rather than infinity terms, there's a last one. What's the last term I would add up in this sum if I'm doing n terms? What do you guys think?
Whatever the nth term is.
Yeah, so like, okay, if n was 100, what would be the last thing I would add up? How would I figure that out?
It would be 1 over 5 to the 100th.
Yeah, it'd be 1 over 5 to the 100th. So if n we just assume is a large number, the last term is 1 over 5 to the nth, like 100 or 100 billion or something bigger than that. But it's whatever n is. Does that make sense to everybody? Okay, what would the term right before that have been? So if this was 1/5 to the 100th, the one before that, if it was 100, what would the one before that be? Yeah, okay, so you guys are saying it in chat. So it's 1/5 to the n minus 1. If it was 100, it'd be 99. But whatever it is, it's one less than that. The one before that would be n minus 2 and on back, assuming n's big. Remember, you have to actually, if it's just S1, you only get these first two. But assuming n is big, you get all these. And the ... just means, okay, this pattern continues until you get to here. Does that make sense to everybody? You guys good? Okay. So now the goal here is to find a quick formula for this where you don't have to add all these up. All right, and so we're going to do something weird, but what we're going to do is we're going to multiply both sides of this equation by 1/5. Okay, so I'm going to multiply both sides of the equation by 1/5. So if I do that on the left, I get 1/5 Sn. If I do that on the right, what is the 1/5 going to do? So I have all this stuff and I'm going to multiply by 1/5. And so I'll write it in red, but I want to erase this later. So I'm going to take this and I'm going to do, okay, times 1/5. What do you do to that algebraically to simplify it? What do you guys think?
You would distribute.
Yeah, you would distribute. So if I distribute 1/5 to this first thing, I get 1/5, right? And just for fun, we're going to write it under this 1/5, but it's coming from this 1. So 1/5 times 1 is 1/5. 1/5 times 1/5 is 1/25. And I'm writing it under here because it matches that one, but this comes from this one. Does that make sense? And then 1/5 times 1/25 is 1/125. 1/5 times 1/125 is 1/625. Does that make sense to everybody? Okay, now, when I do 1/5 times 1/5 to the n minus 1, what happens there? How could I simplify that?
Add the exponents.
You
so
add
just
the
have n.
Yeah, so this is 1/5 to the n because the 1/5 is really 1/5 to the first. Does that make sense to everybody? You add the exponents. So then, okay, 1/5 times this one is 1/5 to the n. And then 1/5 times this last one, what would that be? 1/5 to the what?
N plus 1.
N plus 1, perfect. Okay, now I'm going to erase this red part. But to get the second line, I've multiplied both sides by 1/5. Now, I have made it, so look closely at the screen. I've made it look like these line up. So like 1/5 lines up with 1/5, which is for sure true. 1/25 lines up with this. 1/125 lines up with this. This one I don't have lined up. This one I don't have lined up. But this one I do. And then this one I don't have lined up. So, okay, do these line up? Like, should there be a 1 down here? No, because there was nothing before this. Remember that 1/5 times 1 got me this one. So there's not anything underneath this. Should there be a 1/625, or is there a 1/625 above that one? What do you guys think? Yes. Why is there a 1/625 up here? Even though I didn't write it. Why is there a 1/625 up here?
Because it goes to infinity.
Yeah, well, it goes to n, but n is really big, and this continues in that pattern. Does that make sense? So like the next one in these 3 dots would have been 1/625. Everybody see that? Okay, now what about under the 1/5 to the n minus 1? Is there a 1/5 to the n minus 1 here? There is. Why is there a 1/5 to the n minus 1 here? So there's a 1/625 here. Why is this also going to be here? Because there would have been n minus 2 in here. Does everybody see that? So like the one before this would have been 1/5 to the n minus 2. So then when I distribute, I would have gotten this correct. Or I would have gotten that one. Does that make sense? And then, okay, is there something above this, or is there not a 1/5 to the n plus 1 up here? There's not, because this is Sn, meaning this is the very last one. Does that make sense? Okay, it's important what lines up, because again, if we look at the screen, it looks like this is really complicated. It kind of is, but what we're trying to do is figure out what Sn is equal to. We're trying to get a formula for Sn. So I've got these 2 equations. What would be really smart to do with these equations to make stuff a lot simpler? Something like you might have done with partial fractions or something like that. What could I do with those equations to make things a lot easier? Like given that these line up like this. What do you guys think?
Cancel them out.
How would I cancel them out? What would I do with the equations to make that happen? You're
Doesn't
right.
equal to each other.
Not that, but close. Not divide, but close. Subtract. Yeah. So if I subtract these two equations, then a ton of stuff cancels. So if I subtract on the left, 1 SN minus 1/5 SN is 4/5 SN. Does that make sense to everybody? Okay. Now if I subtract on the right, all of these terms I lined up cancel. Except for these two. So I get 1 minus 1/5 to the n plus 1. And like if n is a billion or bigger than that, all of this middle stuff falls out because you subtract them, they're all the same. The very first one's not, and the very last one's not, but everything else falls out. Does that make sense to everybody? Okay, the whole idea is to find a formula for Sn. Well, Sn then is equal to 5/4 times 1 minus 1/5 to the n plus 1. Does that make sense to everybody? Questions so far? Okay, now we're going to come back to this example, and I want to talk exactly about what that means. But if you look at this one, we could do the same thing. If I go the sum k equals 0 to n of 1/2 to the k, Sn is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/2 to the n minus 1 plus 1/2 to the n. I would then multiply by 1/2 because it would get all the terms to shift. So then I get 1/2 plus 1/4 plus 1/8 plus 1/16 and so on until 1/2 to the n minus 1, 1/2 to the n, and 1/2 to the n plus 1. And now if I subtract them, I get this. And now Sn is 2 times 1 minus 1/2 to the n plus 1. I know that's fast, but does everybody follow what I did there? Okay, so what this does, so I'm going to copy it down just because, well, zoom out a little bit. So what this does is it lets us figure these things out. So like S2, we figured out was 7/4. Well, if I use this formula, S2 is 2 times 1 minus 1/2 to the 2 plus 1. Well, that's 2 times 7/8, which is 7/4. So this is a formula for the terms in the partial sums, in the sequence of partial sums. Does that make sense? Real big deal. So please ask if something's not clear. Does everybody follow what this is getting us? Okay, so like S4, I could get by plugging 4 in here, and it would give me 31/16. Why does this now prove that that we were right when we said this converges to 2? How does this formula down here prove that this does in fact converge to 2? Somebody?
Because when n gets really large, you're just going to be left with 2 times 1.
Yeah, when n gets really large, this part goes to 0, so you're just left with 2 times 1. Does that make sense to everybody? So this series converges to 2. This is a closed formula for any term in the series or in the sequence of partial sums. So if I wanted to find S93, I could just plug in 93 for n, or I look at the limit as n goes to infinity. That tells me that all these things are true. This series converges to 2. So now down here, on the one that's 1/5, what does this series do? Does it converge or diverge? And if it converges, what does it converge to? So as n goes to infinity, what does that do? What happens to 5/4 as n goes to infinity?
Just gets multiplied by 1.
Yeah, it's 5/4 times 1. And then this part goes to 0. So then this series converges to 5/4. Does that make sense to everybody? Questions? Okay, now what we would like to do is not have to do this every single time. So like I said, I do want you to understand this process, and you may have to be able to do this process on an exam. So I do want you to be able to do this, but we don't want to have to do this for every geometric series ever. And so what we're going to do is we're going to do it for the generic geometric series. So a geometric series can always take the form k equals 0 to infinity of AR to the k. So a number times another number to a power. That's the general form of a geometric series. So what we're going to do is we're going to see if we can figure out what Sn is. So if you go back and look, this is not completely unlike this. Like that formula is a lot like this formula, right? And so if we can figure out what happens every time, then we wouldn't have to do this every single time. And so we're going to do this for AR to the K. So Sn is what you get when you go from 0 to n. Well, if I plug in 0, I get AR to the 0. Well, that's just A. If I plug in 1, I get AR to the first. That's AR. If I plug in 2, I get AR squared. I get then AR to the third, and so on. But the very last term is AR to the n, because we're going from 0 to n. What would the one before that have been?
AR to the n minus 1.
Perfect. AR to the n minus 1. Now, back up here, we multiplied by 1/5 to get them all to shift 1. On this one, I multiplied by 1/2. That's the common ratio. It's what you're multiplying by every time. So what you want to do is multiply by the common ratio. Well, what do you multiply by every time here to go from A to AR and then from AR to AR squared? What's the common ratio? R. Yeah, you're saying in chat. Good. So we're going to multiply both sides by R. So we get RSN. And now we distribute R. Well, R times A is AR. R times AR is AR squared. R times AR squared is AR cubed. R times AR to the third is AR to the fourth. R times AR to the n minus 1 is AR to the n. R times AR to the n is AR to the n plus 1. And I know I'm going pretty quick. Do we follow that? Please ask if there's any questions. Okay, now, a lot of this lines up, but some of it does not. Does this A line up with an A that I just don't have written down there? So should there be an A here?
No.
No. Is there an AR to the fourth up here?
Yes.
There is AR to the fourth. Is there an AR to the n minus 1 down here?
Yeah.
Yeah, because AR to the n minus 2 would have been here. And then, okay, is there an AR to the n plus 1 up here?
No.
No, because we're not going to infinity. We're just going to n. And so n's the last term up here. So now if I subtract them, let's deal with the right-hand side first this time. Then I get A minus AR to the n plus 1 because all of the ones in the middle cancel. Does that make sense? On the left, I get the coefficient to be 1 minus r and then Sn. So it's like 1 Sn minus r Sn is 1 minus r Sn. Does everybody follow that? Questions? Okay, so then we're solving for Sn. So we divide by 1 minus r. And we get that formula. This is a real important formula. That's the formula for the nth partial sum of any geometric series, as long as you're starting with k equals 0. So that's the formula for any nth partial sum. This is the same idea as what we had back up here, but we just put the 1 over 1 minus r part in front of here, but the same idea we got here. What part of this not determined that the answer was 5/4, but what part of this determined that this converged, that there was in fact an answer? So what meant that you were going to get an answer here and not like infinity or negative infinity or something else?
Because the n was applied to a number between 0 and 1.
Yes. So this part went to 0. So the fact that that part went to 0, that determined that it converged. So down here, what part of this is going to determine whether or not this expression converges? So like we're looking at the limit as n goes to infinity. Well, what happens to just this a as n goes to infinity? Does that get bigger, get smaller, or just stay the same as I change n?
Stays the same.
That stays the same. The 1 minus r stays the same. This is what determines whether or not the series converges or not. What if r is 5? Not 1/5, but 5. If I go 5 to the infinity, what is this going to do?
It's going to go to infinity.
It's going to go to infinity, which means this whole thing's going to diverge because these are all constants. Does that make sense to everybody? What if r is -6? So -6 to the infinity. It's going to like bounce infinity to negative infinity. That's going to diverge. What would make this converge?
If it's between -1 and 1.
Yeah. So this converges if r is between -1 and 1. And if it does, what does it converge to?
Whatever 1 minus r is.
Okay.
Okay, couple things there. What happens to the part in green if r is between 1 and -1 as n goes to infinity? What happens to this? That goes to just this part. So like if that's 1/3 to the infinity, what's it do? Yeah, 0. So we're saying in the chat, this part goes to 0. So this would go to a minus 0 over 1 minus r, which is a over 1 minus r, if this is true. So it converges if r is between 1 and -1. And if it does, it converges to a over 1 minus r. It diverges otherwise. Now we're going to summarize that. Okay, and that's a really good question in chat. Questions on what we're finding out here? Okay, so the next question in chat, everybody should read that question. Does this still work if the first value of k is not 0? So let's think about that. What if this started at k equals 1? So let's do in this kind of bright blue color. What if this started at k equals 1? What would change down here? So if we're going Sn, it'd be the sum from 1 to n. What would happen at the beginning of this?
You wouldn't have an A, you would have immediately an AR.
Right. You'd have immediately AR. And then what would happen down here?
The AR would go away.
The AR would go away. Okay. So then this is a little different, but this part would still be the same. Does everybody see that? So the part that would be different is what it converges to. So what it converges to changes if this doesn't start at 0. But whether or not it converges is still the same. So it would still converge, but it would converge to something different. And if it diverged, it would still diverge. But the beginning part, so the beginning part of a series is not important in determining whether or not there is a sum. But it does affect what the sum is if there is one. Does that make sense? That's an important distinction to make. Really good question to ask and really important question for everybody to understand. Does everybody get that? Okay, so it would still converge if r is between 1 and -1. It would still diverge otherwise. This would no longer be the sum. It would be whatever this is on the top. So it'd be like, instead of this, it'd be AR. And instead of this, it'd be AR. So it'd be that initial term over 1 minus R. We're actually going to look at that in just a minute. That's a really good question. Other questions? Okay. So I want to look at a few examples. So like I said, this stuff that we've been talking about, doing this like system of equations to figure all this out, that is something you need to be able to do. Okay. So you do need to understand this discussion. But now that we've done it on standard problems, unless you're asked to do this, then we're going to get around it by knowing this final result. And so let's summarize what we've figured out. So we kind of have this big result that for geometric series, if you have the sum k equals 0 to infinity of AR to the k, we know that converges if, and now the most compact way to write that is if the absolute value of r is less than 1. But that's saying that r is between 1 and -1. So that's just a different way to write that r is between 1 and -1.
Would it be less than or equal to?
That's a good question. It's less than. So if it's equal to 1, it diverges. Less obvious, but we'll talk about why that is tomorrow.
Okay.
Back up here, what would happen if r was 1?
Oh, you'd have 0 over 0.
Have 0 in the bottom. So I glossed over that on purpose. And then -1 is something weird to think about. You could probably get it from here, but we're going to look at those examples explicitly tomorrow. I'm glad you asked that, but I did gloss over it on purpose. If it's equal to 1, it does diverge, and we'll get to why tomorrow. It's
Okay.
a little different argument. Good question, though. All right, other questions? Okay, so this is strictly less than 1, meaning back up here, it's strictly between them, not equal to. Okay, and then diverges if the absolute value of r is greater than or equal to 1. And then up here, if it converges, the sum is a over 1 minus r. And just a quick language thing, when you talk about a sequence converging, you call that what it converges to its limit. When you say a series converges, you say what it converges to is its sum. But it's also the limit of the sequence of partial sums. But we normally call the limit of a series, we call this the sum of a series rather than the limit of a series. All right, you guys are asking really good questions. Other questions? Okay, I want to go through a couple examples of just kind of the standard thing you do. So normally we don't do all that because of this result. And so the directions for these are going to be show whether the series converges or diverges. I'm going to abbreviate converges or diverges. And if it converges, find its sum. So this is just like the problems we were doing last week where, or the directions are, the problems are different, but the direction said, show whether the sequence converges or diverges. And if it converges, find its limit. Same idea here, just show whether the series converges or diverges. And if it converges, find its sum. So number 1 is the sum from k equals 0 to infinity of 5 times 2/3 to the k. And so now, we can go through and do that whole system of equations. But now that we've got this kind of big, we'll box it in, this box up here, this result, we don't have to do all that. So you say, as your proof, so what I'm writing in blue is the actual thing you write. So we say, okay, this is a geometric series. Not all series are geometric, but this one is. We know that because it's in this form, AR to the K. Does that make sense? Okay. What about the geometric series determines whether it converges? The value of A, the value of R, the value of K, both or all three or neither, or what? What determines whether or not it converges? What do you guys think? A, R, or K?
R.
R. And more specifically, the absolute value of R. So here we say what that is. The absolute value of R is 2/3. What is significant about that? That it is positive, that it's a fraction, that it's bigger than 1, that it's not equal to 1. What's important about this value?
It's less than 1.
It's less than 1. So you say that. So you say, okay, I know it's geometric. I know the absolute value of R is 2/3. I know that's less than 1. So then the series converges. Okay, everything I wrote there is the quick proof or you showing that the series converges. This first sentence, show whether the series converges or diverges, all of the stuff in blue is necessary for that. And we'll say this a lot, but what you're doing when you're doing series problems is weird because normally in math, you write a bunch of work in order to determine an answer. So like when you're doing an integral, you're trying to find an antiderivative, you do U sub or you do parts and you do all this work trying to get to an answer. When you're doing series, especially when we get to the harder ones, most of the time, you know the answer ahead of time. So like you can look at this and know that it converges and your work is not determining that, your work is showing that you're right. And so you have to write this stuff, even though you're not really figuring it out by doing this, you're showing why you're right about saying that it converges. And later when they get harder, that becomes even more clear that like what you're writing, you're not really figuring much out. You're just trying to prove that what you're saying is correct. Okay. Now, so that converges and now find its sum. So the sum S is A over 1 minus R. A is 5 over 1 minus 2/3. That's 5 over 1/3, which is then 15. And so its sum is 15. Questions on that problem? We're going to do 2 or 3 more and then we'll be good. Everybody good? All right. Problem 2. All right, so I'm actually going to give you about 30 seconds to try that one and then check it with me when you're done. Okay, so when you're looking at this, we should say, okay, this is geometric. The absolute value of R is 7 over 6, which is bigger than 1. So the series diverges. And we're done. You can calculate the sum, the S, but that is not the sum of the series. When it diverges, it goes to infinity, or it goes to negative infinity, or it bounces infinity to negative infinity. So calculating this means nothing, even though you can get an answer for that. It is not the sum of the series. So especially when you're doing like a test or something, do not calculate that because it looks like you don't know what you're talking about because you're finding a sum that doesn't exist. When you say it diverges, that means there is no sum. It's okay if you did it this time, but don't do that. Cross that part out. All right, questions? Okay, so number 3. Number 3 is the sum k equals 2 to infinity of 3 times 1/3. Let's not make it 3, my bad. Let's make it 8 times 1/3 to the k. All right, so again, I'm going to give you about 30 seconds to try it and then check it with me when you're done. Okay, so when we're doing this, we should say, okay, it is geometric. The absolute value of r is 1/3, which is less than 1. The sum is 8/9 over 1 minus 1/3. That's 8/9 over 2/3. That's 8/9 times 3 over 2. These cancel. And this converges to 4/3. There should probably be questions on this one.
I thought that k had to equal 0 to be geometric.
Okay, good question. K does not have to be 0 to be geometric, but K does have to start at 0 for this formula to work the way that it seems like it would. Does that make sense?
Yes.
Okay, so it's still geometric, but something weird happened on this sum.
Yeah, so why does having a k of 2 put it at 8/9?
Yeah, so if you go back up and look at this, remember the reason it's a over 1 minus r is because what I crossed out, that a is what's left over. So what's left over is whatever the first term is in this expansion. Does everybody see that? Okay, the reason that it's normally a is because if I plug in 0, I get ar to the 0, which is a. If I were to plug in 1, I get ar, which is ar. That would then be the first term. So the generalized idea here is the sum is this a when k is 0. But in general, it's whatever the first term in the expansion is. So you plug in the first value of k to figure out what this numerator is. So if I plug in 2, I get 8 times 1/3 squared, which is 8 times 1/9, which is 8/9. Does that make sense to everybody?
So would a better way to write this be AR to the K over 1 minus R?
You could write it that way, James. Yeah, sure. So if you wanted to write it as AR to the K, you could do that. It's a little bit misleading because this A doesn't have to match that A. This is the standard way to write it because in this formula, it's correct, but it's whatever you get when you plug in this first value of K. It's also still that, like if I plug in 0, it's 5 times 2/3 to the 0, which is 5. So what you want to do is get in the habit of, okay, I know it's this A over 1 minus R, but this A is really whatever that first term in the expansion is. However you want to write that or remember that, I'm okay with. We write it like this so that it's like formally correct. But when it's not k equals 0, you just have to modify the approach. Does that make sense?
So like on a test,
Yeah.
for the sake of our ability to maintain a thought process, if we were to write
Yeah.
something like AR to the k sub 0 to indicate that it's the first k value.
I would stick with A over 1 minus R because you're not writing this. You see what I'm saying? So like the only problem with what you guys are saying is that this A doesn't match this A unless K is 0. But you're never writing the letter A when you're doing a problem. Do you see what I'm saying? So
Okay.
if it were me, I would memorize, okay, A over 1 minus R and just think, okay, A is not really this. A is the first term of the expansion. That's what I think is the easiest approach. But whatever works for you is fine. You're not using the letter A within these proofs anyway. Do you see what I mean?
Okay.
Okay. Does that help? I'm trying not to make it worse. I'm trying to make it easier. That's good.
Yeah, no, that's not bad.
Okay. Other questions so far? Okay. Now this is going to build a lot. And so what I need you guys to do, so right now there's no WebAssign, and there's a good possibility that there will be no WebAssign for now, because I'd rather you do the written homework. The problem is I give you the solutions, and so you've got to actually do the written homework. So what I want to show you is on this series 1 worksheet tonight. So it's just these. So prove or show whether the series converges or diverges. If the series converges, find its sum. This is in Unit 3, Folder 2, which was posted probably an hour ago. If you go in there, this is a 5-page packet, and then you also have solutions to this. I need you to do the first 5 problems before tomorrow. Okay, so you're not handing it in or whatever, but like if you start to fall behind, this is going to get really, really hard. So the first 5 problems are just like what we just did. They do not all start at 0. So straighten that out. Check with my solutions. Make sure you understand them. And if you don't, let me know, and we'll go over them. Like I'll try to be on before class tomorrow. I'll try. I have a class right before this, but I'll try to sign on a few minutes before class. So if you want to come in 5-10 minutes early and go over any of them, we definitely can. But this is going to build a lot tomorrow. So make sure you're good with this today. All right. That is it for today. If you have any questions, stick around. If not, I will see you guys tomorrow. Thanks for coming, you guys.